Physics Part 182. This representation is tedious to draw, and figure is the conventional way of showing the amplitude of vibration. The amplitude along the axis of the tube are plotted as a continuous curve. One danger of using diagrams like this figure is that they give the impression that the sound wave is transverse rather than longitudinal. So be warned that the mode illustrated in the figure is the fundamental mode, the first harmonic. The wavelength of the stationary wave, ignoring the end correction, is 4L, where L is the length of the pipe. Using the wave equation, the frequency F1 of the fundamental mode is given F1, which is equal to C over 4L, where C is the speed of sound in air. Other modes of vibration are possible. The figures show the second mode, the first overtone or the second harmonic, and the third mode, the second overtone or the third harmonic. The corresponding wavelengths are 4L over 3 and 4L over 5. The frequencies are F2, which is equal to 3C over 4L, and F3, which is equal to 5C over 4L. The general expression for the frequency Fn of the nth mode of the vibration of the ear in the closed tube is nth harmonic, or the n minus 1. The overtone is Fn is equal to 2n minus 1 into C divided by 4L. This is another example of the resonance. The particular frequencies at which stationary waves are obtained in the pipe are resonant frequencies of the pipe. Stationary waves using microwaves. The stationary waves can be demonstrated using microwaves. The source of microwaves faces a metal reflecting plate as shown in the figure. A small detector is placed between source and reflector. The reflector is moved towards or away from the source until the signal picked up by the detector fluctuates regularly as it is moved slowly back and forth. The minima are nodes of the stationary wave pattern, and the maxima are the antinodes. The distance moved by the detector between the successive nodes is half the wavelength of the microwaves. Measuring the speed of sound using stationary waves. The principle of resonance in a tube closed at one end can be used to measure the speed of sound in air. A glass tube is placed in the cylinder of water. By raising the tube, the length of the column of the air can be increased. A vibrating turning fork of known frequency F is held above the open end of the glass tube, causing the air in to vibrate. The tube is gradually raised, increasing the length of the air column. At a certain position, the note becomes much louder. This is known as the first position of resonance and occurs when a stationary wave corresponding to the fundamental mode is established inside the tube. The length L1 of the air column is noted. The tube is raised further until a second resonance position is found. This corresponds to the second mode of vibration. The length L2 at the position is also noted. The two resonance positions are illustrated in the figure. At first, the position of resonance lambda divided by 4 is equal to L1 plus E, where E is the end correction of the tube to allow for the fact that the antinode is slightly above the open end of the tube. At the second position of the resonance,
One